Okay, so let's look at some examples of how we determine something called the pH. So the pH is what we use to determine the acidity or basicity of a solution. So it tells us how acidic or basic a solution is. pH, P stands for potential hydrogen. We are mostly gonna, we'll talk about both acids and bases, but the pH scale goes from 14 to 1 with 7 in the middle. So at the top of this scale, 14, we have a base. At the bottom of the scale at 1, we have acids, and things that are in the middle at 7 are neutral. So if there is a pH that is between 1 and 7, that is considered acidic. Between 7 and 14 is considered basic. There are some weird examples of bases that have a pH higher than 14 and acids that have a pH lower than 1. We're not going to worry about those. So the way that we calculate the pH equals the negative log of the hydronium ion concentration. That is the way we calculate pH. So you need the hydronium ion concentration to solve for the pH. So essentially, let's see what this actually means over here. So acids are going to have a very high hydronium ion concentration, and they would have a low hydroxide ion concentration. So you can just ignore the hydroxide ion part for right now. If it's neutral, the hydronium ion concentration is going to equal the hydroxide ion concentration. Remember, the hydronium part is the acidic part, and the hydroxide part is the basic part. If it is 14, or if it's basic, then it would have a low hydronium ion concentration, and it would have a high hydroxide ion concentration. However, the pH scale is only based on the hydronium ion concentration. There is another term which is called the pOH, which is much less common. The pOH is the negative log of the hydroxide ion concentration. We'll talk about that later. But this is just the relationship between the hydrogen ion equals hydronium ion. So depending on how you see this written. But whatever the concentration of the hydronium ion is, you take the negative log of that to get the pH. So it's an inverse relationship. The higher the concentration of hydronium, the lower the pH, because this is a negative log relationship. So something that has a very low pH would have a high hydronium ion concentration. So let's look at all the different formulas that we could potentially use. We could say pH equals the negative log of the hydronium ion concentration. If you are given the hydronium ion concentration, then that's what you would use. If you are not given the hydronium ion concentration, if you're doing the opposite, if you wanted to solve for the pH, you could say hydronium ion concentration equals 10 to the negative pH. This is just the inverse. And conversely, if you were talking about pOH and hydroxide, you could say the hydroxide ion concentration equals 10 to the negative pOH. So all of this also has to do with the kW of water. So remember, we learned that the kW of water is 1 times 10 to the negative 14th, and we know that that is always hydronium times hydroxide. So the product, the ion product constant of water, is always 1 times 10 to the negative 14th. So if you're given the hydroxide ion concentration, you can always solve for the hydronium, and because you know that the product of these two always equals 1 times 10 to the negative 14th. So this is the information that you need to do these pH calculations. So let's look at an example. Let's say, what is the pH of a 0.10 molar solution of hydrochloric acid? So we know that HCl is a strong acid. Remember the lists of strong acids: HCl, HBr, HI, HNO3, HClO4, H2SO4. So these all ionize completely, which means that this is a 1-to-1 ratio. So if I have 0.1 molar HCl, that means I also have 0.1 molar hydrogen. So let's look at that. HCl is going to ionize completely into H plus and Cl minus. So if I have 0.10 molar HCl, it's a 1-to-1 ratio, 1 mole of HCl, 1 mole of hydrogen ion, which produces the hydronium ion. HCl will cancel. I will have 0.10 molar hydrogen. Remember, hydrogen and hydronium, they're interchangeable because this hydrogen is going to find the water. This is an aqueous solution, and it's going to have that same concentration of hydronium. The reason that I know this is because this is a strong acid, because it ionizes completely. I can use the stoichiometry of this reaction to see if this is the concentration of the strong acid, what is the concentration of the hydrogen? So I'm just going to rewrite this as 0.10 molar hydronium. So now if we're asked for the pH, now I have the concentration of hydronium. I have the concentration of hydronium because I was able to see that this HCl would break apart completely. So however much HCl there is, that is also the same amount of hydronium that's produced. Okay, so now if I want to solve for the pH, I'm just going to say pH equals the negative log of the hydronium ion concentration, 0.10. So if I take the negative log of 0.10, negative log of 0.10, the pH is 1. And if I look at this concentration, then that has two significant figures. So the pH is 1.00. So now this is a weird pH significant figure rule. It's actually not a pH rule, it's a logarithm rule. The rule is the number of significant figures in the concentration is the number of decimal places in the pH. So again, this isn't really a pH rule, it's a log rule. The number of significant figures in the number you're taking the log of is the number of decimal places in that value in the pH. So for example, this number has two significant figures, 0.10, so your pH has to have 2 decimal places. This is something that is really important because you will lose points on all of the SmartWorks homeworks and all of the lab exercises for significant figures. So make sure that you understand this. Anytime you're taking a log, the number of significant figures that you took the log of is the number of decimal places in the answer. So the pH here is 1.00. If on SmartWorks or in a lab you put 1.0, it would be marked incorrect because it would have the incorrect number of significant figures. And significant figures are very important in the lab, especially because they determine a lot of other statistical values. So the pH of a solution of 0.1 molar HCl has a pH of 1.00. So let's look at another example. Let's say 3.52 grams of hydrogen bromide is dissolved in 500 milliliters of water. What is the pH? Okay, so what we need is the concentration of hydronium or hydrogen. We don't have that. We have a mass of hydrogen bromide and a volume of water. So what we need to do is we need to first determine how many moles of hydrogen bromide are in 3.52 grams, and then from there find the molarity. And then once we have the molarity, we can solve for the pH. So I'm just going to write down what I'm going to do. I am going to convert 3.52 grams of hydrogen bromide to moles of hydrogen bromide. Then I am going to solve for the concentration of hydrogen bromide. Then I will solve for the concentration of hydrogen or hydronium, same thing. And then I will solve for the pH. Okay, so I have 3.52 grams of hydrogen bromide. The molar mass of hydrogen is about 1. The molar mass of bromine is about 79.90. So I'm just going to say 80.90 grams of hydrogen bromide in 1 mole of hydrogen bromide. So grams of hydrogen bromide are going to cancel. So if I take 3.52 divided by 80.9, I have 0.04, let's see, 3 significant figures, 0.0435 moles of hydrogen bromide. So that was step 1. Step 2 is I'm going to convert the number of moles of hydrogen bromide to the molarity of hydrogen bromide. So remember, molarity is moles per liter. So I have 0.0435 moles of hydrogen bromide, and I have 0.500 liters. Because remember, this is in milliliters. Convert milliliters to liters. This gives me a molarity of 0.0870 molar. So this is the concentration of hydrogen bromide. Remember, hydrogen bromide is one of the 6 strong acids, which means it's a 1-to-1 ratio. Hydrogen bromide is going to ionize completely into hydrogen ions and bromide ions. So if I have a concentration of 0.0870 molar hydrogen bromide, and 1 mole of hydrogen bromide is going to produce 1 mole of hydrogen ions, that means I have 0.0870 molar hydrogen ions. So now to solve for the pH, I'm going to take the negative log of the concentration of the hydronium ion. pH equals the negative log of the hydronium ion, 0.0870, pH equals 1.06048, whatever. So again, remember the rule. The number of significant figures in the number you take the log of is the number of decimal places in that answer. So this number has 3 significant figures, which means my answer needs to have 3 decimal places. So the pH is 1.060. This is the pH when you combine 3.52 grams of hydrogen bromide in 500 milliliters of water. Again, remember that the number of significant figures, 3 significant figures in the number you're taking the log of, is the number of decimal places in your pH, 3 decimal places.